Now, I present you now the iteration method, which is called the D-iteration, D-OS, diffusion-based approach. So, as the input of this problem, I need a matrix P and B, which is the initial condition. And so, P, I just assume that spectral radius is 6 less than 1. That's all I need. And then from this, I can define a method of diffusion, which is fluid. So, fluid in the sense of not a limit, but really fluid water. Fluid. So, and I show you why you have these images behind them. So I just, to illustrate the algorithm, I won't give you the pseudocode or something like that. I just illustrate through a very basic example, but from the basic example, you will very easily understand. I take P like this. Why this? Because this is simple. So just take this. And B, anything. One everywhere, just to simplify. So this is the case. The dimension of the problem is n equal to 3. Okay? Square matrix, 3 times 3. So first, I consider 3 nodes. So I start by constructing the graph, which is associated to the matrix. So the association is very straightforward. It's very easy. If you have a link between 1 and 2, and the link is defined by the coordinate. So the way you read the matrix, since I did a P times X, not X times P, you have to jump from 1 to 2. You have to go to column 1 to line 2. Okay, to have to win the way. So because I had this equal to 0.5, this I put a link with the weight corresponding to this value. And if the weight is 0, you have to have link. Okay.
Sorry. Just a short question. Why do you transform into a graph?
Just to show you more easily the intuition behind. But I could give you the pseudocode of the matrix, but this is much more intuitively easy. And so this everybody understand, it's quite clear. Just remark. Here everything is positive, because playing with a fluid positive is more, or all the same sign is more intuitive, but you can mix. And since the condition is the spectral radius of P is strictly less than 1, you can mix negative and positive, both for B, and also for coefficient of P.
And because a question about P, because I see that the diagonal is 0, and I guess that your P is...
the diagonal is not 0.
In P, the matrix?
No, in the general case, what I need is you want to solve find x such that x equal to px plus b, and P satisfies just one condition, which is spectral radius 6 less than 1, which doesn't mean that diagonal term is equal to 0.
Okay.
Just when I had a transformation from Ax to equal to B, the way I did it.
Yeah, because I see that there are some cases in which you have the identity, and you subtract from the identity.
Yeah, but just to explain the transformation, the equivalence to the other class of problems. But in my case, I don't need any condition at all.
Just an example.
Yeah, and also indeed here I didn't put C, but I could also put. You see that in terms of understanding the problem, you see clearly from it. So first step, what I do is at each node, I don't know how you say that in English, a recipient, something like that. You associate something like that, a recipient, on which you can put something. And you have some controller, you can open or close. And here you have a counter. So it's like a water counter you have at your home. Every time there's a fluid going through, it counts. So first step, I fill the recipient with the fluid, which is the initial vector condition, which was B. So in this particular example, it was 1 everywhere. Next step, I have to choose one of the 3 nodes. So this is the open problem. I'll go back to that. This is the open problem in terms of optimization problem. But assume that you have a way to choose. So I choose this node 2. Why not? And then what I do is first, so I open the control. So the fluid go down. But then the counter is implemented by 1. Okay. Then this fluid I diffuse. And the way I diffuse, I just follow the link. Here, you just have this link going out. This weight 0.5. So what it means, I made this disappear and put it like this, applying this coefficient, so that you have this situation. I added 0.5. Okay? And then just I'll repeat this infinitely. Second step, for instance, I choose this node. So I open, it's already signed. It's open, so the counter is incremented, and then it's sent through this 0.5. And then I can start again, choose this one, and it's sent. One thing you may remark already, what's essential as property is that every time you do this kind of operations, so this here you apply this 3 times, okay? And if you look at the counters here and counters here, oops, there's something missing here. I forgot to put this was supposed to be. I'm sorry. This is here, okay. If you do some this plus this, of course this is still less than the initial value, which was 3, 1 plus 1 plus 1. And the condition spectral address of P 3 less than 1 guarantee that if we iterate that asymptotically, the all fluids will disappear, the fluids which are here, and the counters will be all finite quantity. And if everything is positive, this component by component is a strictly increasing function. Okay? Yeah.
Why is it 1.5?
Yeah.
The counter, why is it 1.5?
It just counts all fluid which is.
It counts the quantity of liquid. It doesn't count the other stuff. Okay, you just add the number, the quantity of fluid.
Each time this node is chosen and if you send fluid, you just add the counter.
Loïc, there may be something I didn't understand. You have 0.25 in both parts.
Yeah.
Why not you have the same number then?
This comes from matrix P. This is a bit from matrix P, which is the example I choose here, which is sorry.
You already had 0.5. Sorry.
Okay.
Okay, I forgot it.
Yeah, so the sum of all fluids is decreasing. This is important. And of course, if you have something which is like the condition like diagonal dominant, for instance, this is for diffusion. So diffusion means that you send to others from one node. So this is the version of a diagonally dominant system for each column, and in this case, operation per operation, you have a reduction. Okay, that's we need a difference. Okay. For instance, here I have 0.20. If you have just a tooling like that, here you could have, for instance, a value which is higher than you could have an increase locally of width. You could have a 2 here. Here, for instance, I come back with operation which is 1/4, which is globally. How do you say? Spectral radius is less than I don't know how to say. Okay, and if you iterate in this particular case infinitely these operations, when the all fluid in the recipient is equal to 0, you get this value. So this here I just give you this value, and I come back to these values, and the object of interest are these values, and these values are such that it solves this equation. So that's the main property of this decision method. So I guess in terms of what I do in the iterations is clear for everybody. I just choose nodes, I diffuse, and just iterate. Up to the time, there's no more fluid. Okay? And this asymptotically solves this equation.